You know about this. I don't think you'll have too much trouble finding the location. And for those of you who have a legitimate conflict on Thursday evenings, say for example you have 46 laboratory, whatever, I need a note from you indicating the nature of this conflict, email address, and an indication of when you can take the exam earlier on in the day. The earlier time slots are any of these three. Your choice. But this information must be given to me by a written note, not email. Now, chapter 19, a couple of final considerations. Calcium carbonate. We've considered the solubility, now stability of calcium carbonate under a number of different conditions. Imagine we wish to know about the solubility of calcium carbonate in a solution in which the calcium ion concentration is made to be 0.10 molar by adding an external source of calcium ion, like calcium chloride solution, versus the solubility, stability of calcium carbonate in a second solution in which we've adjusted the carbonate ion concentration to be 0.10 molar by adding an external source of carbonate ion like sodium carbonate solution. Calcium carbonate is more stable, less soluble in the 10th molar carbonate ion solution than it is in the 10th molar calcium ion solution. Why?
Isn't it also because that the carbonate will also drive up the pH and it's more stable in the basic environment?
Well, there's no question that the carbonate ion's presence drives up the system pH. What impact does that have on calcium carbonate stability?
When it drives the equilibrium.
Which equilibrium?
That produces between calcium carbonate and water. Water to form calcium ions and
do you recognize that to answer this, you have to look past this equilibrium?
When you increase the calcium concentration, you decrease the carbonate concentration, and carbonate reacts with water.
Wait. We got two different systems. Let's try it this way. In this beaker, I have 10th molar calcium chloride solution. In this beaker, I have sodium carbonate solution at a concentration at which the molarity of carbonate ion is 0.10 molar. So M sub I is going to be a little bit larger than 0.10 molar. Why is that true? Why is it that if I want carbonate ion to be present in solution at 10th molar, I've got to have the sodium carbonate, which is my source of carbonate ion if I'm using sodium carbonate, to be at a little bit higher M sub I value than 0.10 molar?
Because some of it's going to react with water.
Because carbonate ion does something that calcium ion doesn't do. What's this something?
It affects pH.
It's called, what's the name of the reaction?
Ionization.
Better. Ionization is okay, but what's better?
Association.
We're talking about something reacting with water.
Hydrolysis.
Hydrolysis. You betcha. And that's the answer to this question. In the 10th molar calcium ion solution, carbonate ion still hydrolyzes. What's the impact of carbonate hydrolysis on calcium carbonate solubility? Does carbonate ion hydrolysis cause calcium carbonate solubility to go up or come down? Increase or decrease? Why can't we calculate the solubility for calcium carbonate straight from this reaction? Why is it that the solubility of calcium carbonate is not the square root of its KSP in straight water?
You have to consider the different forms of carbonate, which will...
Be specific on this. What does carbonate do?
Carbonate will hydrolyze.
Yes. And the impact of that what's the impact of that on calcium carbonate solubility? We've been doing this. The calcium carbonate solubility in water is 1.4 times 10 to the minus 4 molar. Here's KSP. You should see at a glance that the square root of KSP is a lot smaller number than this number. So the impact of carbonate hydrolysis. What did we do to the solubility of calcium carbonate when we put it in a system of pH 6 versus pH 8? pH 8 versus DIW. What happened to solubility every time we made the system more acidic? The solubility increased because we have hydrolyzed carbonate more effectively. You killed it more effectively. So hydrolysis increases solubility. So if we stop hydrolysis, we reduce solubility. You're not stopping carbonate hydrolysis in 10th molar calcium ion solution. But if I enrich the solution with carbonate ion, hey, I'm stopping carbonate hydrolysis as a consequence of carbonate ion being put in solution by this reaction. You do the arithmetic. Another question. Same idea, really. Why is calcium carbonate more stable in deionized water than it is in 1.0 molar sodium hydroxide solution? Well, I shouldn't have said same idea. It's not the same idea. We have reminded ourselves that if you stop carbonate hydrolysis, you reduce calcium carbonate solubility. You make calcium carbonate more stable. You think you're going to stop carbonate hydrolysis? By dissolving calcium carbonate in 1.0 molar sodium hydroxide solution? You're damn right. Yet, calcium carbonate is more stable in deionized water than it is in 1.0 molar sodium hydroxide solution. Now watch out. I didn't use the word soluble. I used stable. What happens in the 1 molar sodium hydroxide solution that does not happen in straight water?
Doesn't it create calcium hydroxide?
Yeah. Now you're going to convert some of the calcium carbonate to calcium hydroxide. And that reduces the stability of calcium carbonate. Anytime you increase the tendency for calcium carbonate to react and become something else, you've lowered its stability.
Is that related to the salt effect at all?
No, not in this case. Well, I don't think so, because hydroxide ion is an integral part of the carbonate ion hydrolysis reaction. Now, I'll go on to tell you, and you can do the arithmetic to verify this, that in half molar sodium hydroxide solution, now the calcium carbonate is more stable in the basic solution than in deionized water. Now what do you think's going on in the half molar sodium hydroxide solution? Or maybe I should say not going on in the half molar sodium hydroxide solution that's going on in the 1 molar sodium hydroxide solution. In which of these solutions will I more effectively convert calcium carbonate to calcium hydroxide? The more concentrated sodium hydroxide solution. So in this case, the main impact of the high molarity of hydroxide ion is to stop the hydrolysis of carbonate ion. But it's not high enough to convert calcium carbonate to calcium hydroxide. in substantial quantity. You do the arithmetic. It's not hard. What reactions do you have to pay attention to? You got to pay attention to this reaction. Calculating K for this reaction is easy. What is K for this reaction?
Concentration.
Well, you can say concentration, but you should tell me straight away, what is K equal to for this reaction? Try again. Is this reaction composed of 2 semi-soluble salts of calcium ion? Calcium carbonate, calcium hydroxide? So K for this reaction is KSP calcium carbonate divided by KSP calcium hydroxide. Done. You've got to let these reactions talk to you. Chemistry is what counts, and that's what we're talking about. The reason why this problem is no longer difficult, at least from my perspective, is we've talked to you about the chemistry you need to pay attention to. Rest is arithmetic. Now, beside this, what other reaction do you have to pay attention to? Remember, we're taking a look at the possibility of preventing carbonate from hydrolyzing. In case you didn't get it for this 10th molar carbonate system, there we're just fixing the carbonate at 10th molar. So forget hydrolysis. But now to the second case. By enriching the system with hydroxide ion, we're stopping carbonate from hydrolyzing. But by enriching the system with hydroxide ion, we're also giving the possibility of calcium carbonate to react with hydroxide ion and become calcium hydroxide. Okay? Hydrolysis, as well as the possibility of converting calcium carbonate to something else, each reduce the stability. Each effect, hydrolysis, converting calcium carbonate to something else, each lower the stability of calcium carbonate. So beside this, you got to look at this to get a handle on calcium hydroxide that you're going to make. In other words, I'm just making a point that you've got to pay attention to KSP for calcium hydroxide, which of course is an integral part of this reaction. You do the analysis and it'll talk to you. If you don't do the analysis, it'll never talk to you. On we go. Chapter 20. Which is what we have been doing since day one. Nothing but chapter 20. Chapter 21. Fundamental thermodynamics, that's all we've been doing. To this point in time, you think it's a fair statement on my part that we have paid rather extensive consideration to equilibrium systems? That sound like fair? 2045 ought to teach you that equilibrium is strictly a province of thermodynamics. It follows from kinetics. When for a reaction system, the rate of the forward reaction and the rate of the reverse direction are equal, system's in equilibrium. But when you're in equilibrium, kinetics doesn't mean a damn thing anymore. Now it's strictly thermodynamics. And that's all we've been doing so far, because practically speaking, the only types of systems we have so far analyzed are equilibrium systems. And those are the only types of systems practically we're going to continue to analyze. The real nuts and bolts of kinetics is above and beyond what we can deal with successfully in general chemistry. You've had an introduction to this by 2045 lecture, by 2045 laboratory, the last laboratory experiment on decolorizing blue food dye with household bleach. But legitimate kinetic studies oftentimes require very sophisticated arithmetic analysis and experimental gadgetry, which is far and beyond what we can make available to you in the general chemistry laboratory. Not much is done in any undergraduate course or laboratory that I'm familiar with on kinetics. It's too difficult. But important? You're damn right it's important. Most of the chemical processes upon which our life depends are controlled by kinetics rather than thermodynamics. So do you think it's fair to say that we ought to be learning about these things? I mean, presuming we care about our life and well-being? All right. Now, as I have remarked previously, the shortcoming, the serious shortcoming of general chemistry textbooks, which offer a chapter early on in the book, it's usually chapter 5 or chapter 6, on change in enthalpy, or enthalpy and change in enthalpy, heat flow, is that you cannot get at reaction spontaneity by considering change in enthalpy only. And what we want to know about a reaction is, under the conditions that the reaction is being studied, can it go? If it can go, the thermodynamic term is spontaneous. That doesn't mean it will go, but it can go. On the other hand, if we find for the conditions that the reaction is being studied under, the reaction cannot go, then that's the end of it. You'll have to change the conditions in some fashion for this reaction to go. See this stuff? Wood fiber, commonly called paper. This stuff is obviously stable in this air atmosphere, isn't it? Because I have it here, just like you've had your notes with you for a good long time. Is this stuff stable in air atmosphere thermodynamically? Yes or no? Yes. Absolutely not. You should have done this in 2045. Because I know in 2045 you paid attention to information in thermodynamic properties data table. But I'll bet all you did with it was a bunch of arithmetic by use of Hess's law, rather than understand what the hell that information means. That's what counts. I'm talking specifically about Table 1 at the end of Chapter 20 in our notes, which is a collection of information that I've taken from the National Bureau of Standards publication. Thermodynamic properties of common substances. There's more chemistry in that table than in any other single tabulation or book that you can find in the universe. Take a look at that table. If you use the information in that table and recognize, well, I'll ask you, if I get this stuff to start to react in air, what do I do to get this stuff to start to react in air? Still stable, isn't it? Is it getting less stable? Getting less stable? What did I do just then?
You brought it up to a temperature at which combustion is spontaneous.
No. The combustion of these things in air is spontaneous at this temperature. What barrier did I overcome with what I just did? Activation energy, you betcha. The kinetics of the system stops it from going. Paper is stable in air because the rate of reaction is so damn slow that practically speaking it doesn't go. But you heat it up and you see that it goes. And how do you recognize, after I heat it up and get this combustion process started, how do you recognize that the reaction that we're talking about, the conversion of cellulose molecules by combination with oxygen molecules from the atmosphere, converting to what? What do we make when we burn paper? Carbon dioxide gas and water. If you analyze this thermodynamically, you'll find out that the change in enthalpy is very much for this process. It's a highly exothermic reaction. Do you believe that? Can you heat your home by burning paper? Can you heat your home by burning wood? Hell yes. Because after I get this reaction started, do I keep have to adding lit matches? Hell no. That's what's showing you it's spontaneous. Once you get it started, it keeps on going. Because now it keeps supplying itself its own activation energy requirements. How about that? Simple. This is the kind of stuff you should do in 2045. So you understand what the hell's going on. That's what you do in my 2045 class. And I hope sooner or later we get that done in all 2045 classes. So you know what the hell this stuff means. Now then, from an arithmetic standpoint, to determine reaction spontaneity, we need to employ these relationships. You'll find these relationships derived in the notes, chapter 20, when you get into about, I don't know, page 6 or 8 in chapter 20. I don't hold you responsible for the derivation. I don't hold you responsible for memorizing the 3 laws of thermodynamics. If you need to use that information, I'll give it to you. That's your job. Be able to use it, not to memorize it. 4th grader can memorize a whole bunch of stuff. That doesn't mean a 4th grader can understand it. This delta G is the thermodynamic criterion for reaction spontaneity. If, for the reaction under consideration, the calculated value for delta G is minus, spontaneous, it can go. If delta H is minus, that supports the possibility of delta G being minus. If delta H is minus for a reaction, what's that mean? Is the reaction exothermic or endothermic? Exothermic. Energy liberating. Do you think I'm becoming more stable if, as I react, I'm getting rid of energy? You're damn right. Such reactions are driven because of delta H, exothermic. Now, there's another part to this puzzle. The part that textbooks don't talk about. Stupid damn things that they are, and I mean it. I'm serious about this. It's this part. Now this part is a little bit more difficult to understand from an idea standpoint, conceptual standpoint. But so what? It's still got to be considered so we can get at this. For now, we'll just call this the mix-up factor. We'll elaborate on this mix-up factor called entropy as our conversation proceeds. Tell me, if a reaction is exothermic, what do you know about the stability of the reactants compared to the stability of the products for an exothermic reaction?
Products are more stable.
Yes. Specifically from what kind of standpoint? What is the enthalpy of a stuff measure? Don't tell me heat content, because I can't contain heat.
the energy in the bond, stored in the bonds between atoms.
Bond strengths. Yeah, that's what enthalpy measures. So what you're finding out, if a reaction shows itself to be exothermic, is that bonds have been improved. Bonds either got stronger or you made more of them or both for an exo reaction. That's what counts. And I still haven't found a textbook that says this. I don't get it. Chemists are materialists. Not from an economic standpoint, but from a science standpoint. We study matter and its properties. Exo reaction, the products are more stable than the reactants because bond strengths products greater than bond strengths reactants, vice versa. Endo reaction, bonds are weakening as we convert reactants to products. That's why you got to put the energy in. You know daggone well. If you want to weaken bonds in matter, you heat it up or cool it off. If you want to defeat hydrogen bonds, like in a sample of water, how do you defeat hydrogen bonds? You put the water in the refrigerator freezer, or you put the water in a pan on a stove and heat it up and boil it. And pull the water molecules apart, thereby breaking the hydrogen bonds. Heat it up. Now, the problem with this, from an analysis standpoint, is this relationship applies to any imaginary set of conditions. Not imaginary, pardon me. Any possible set of conditions. Like, for example, we know calcium carbonate isn't very soluble in water. I should think if there's anything we know that. Yet if I take pure water and add to it pure calcium carbonate, does the calcium carbonate dissolve spontaneously? Yes or no? You're damn right. There's nothing else that can happen except the calcium carbonate dissolving. And it dissolves until the molarity of calcium ion is this. That's not much. But nevertheless, combination pure water, pure calcium carbonate at normal lab conditions, the calcium carbonate dissolves until the calcium ion molarity becomes this. And you didn't do anything but with calcium carbonate in contact with water. Spontaneous. So, in order to be able to pinpoint spontaneous, we use this relationship. You've seen this relationship. This means let's pay attention to the change in free energy for the reaction, but under a specific set of conditions designated by this superscript 0. What's that mean?
Isn't it specific?
What's the superscript 0 denote? You did this in 2045, I hope. What does the superscript 0 denote? Designate. What kind of conditions? Standard conditions. What are standard conditions? What do you mean 1 atmosphere? Not enough.
Standard lab conditions.
We'll talk more about that in a moment. But I guarantee, if you wish to be able to fare well on coming exams, you damn sure better know how to establish standard state conditions. And after I get done with you, you will. Now then, some examples. Spontaneous. We talked about paper and air. Thermodynamically, totally unstable. A conversion of paper in the presence of oxygen under these conditions to CO2 in water is spontaneous. This drives it and this drives it. They're both for it. It's a favorable change in entropy as well as a favorable change in enthalpy, which means exo. Now, conditions. All right? Water. Deionized water. Some phenolphthalein. Just to see what happens to system pH as we run this transformation. Natrium. You're all familiar with natrium, aren't you? Where the hell do you think that symbol Na came from? How do you get sodium out of Na? Huh? That's the old Latin name for the stuff. K. How do you get potassium out of K? Kalium. The old Latin names. Okay? Does natrium react spontaneously with water under these conditions?
Yes.
Are you sure?
Yes. Very good.
Let us have a chunk of natrium. Ha 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 ha. Natrium. Ooh, I like this stuff. It's stored under kerosene, and I'm going to try to prevent the kerosene from becoming part of this observation that we now wish to make. So I'm mopping off the surface of the sodium with Kim wipes. Where'd you go? There you are. Did you know that in World War I, the Allies' first attempt at making depth charges to get to U-boats was to fill up big drums with natrium? I got to get ready for my getaway. Goodbye. You see the natrium zipping around the top of the water? The system is becoming a flame has become part of the system. What do you think's burning? That's right. Oh, usually it goes pow and blows my lid off the top. That's why the lid that I have is made out of plastic so it doesn't shatter. I used to do this with glass, but the people around here got mad at me because they kept having to clean up the mess I made. All right? Would you agree that was spontaneous? What did I do? Put the sodium in contact with the water and got the hell out of the way. Nature took care of the rest. Okay? Now then. One or more of you observed correctly or decided correctly that the flame which we saw was a consequence of the heat of this reaction, because this reaction is exceptionally exothermic, ignited the hydrogen that was produced, because in here there's also some oxygen. Okay? Now, you also see that the system became basic, because as sodium reacts with water, beside producing hydrogen and sodium ion, what else do we produce? Hydroxide ion. That's why the system got basic. We're going to do this again in chapter 22 on electrochemistry. But now back to this spontaneous business. All right? Hydrogen and oxygen. Oh, we just saw that if you get the hydrogen ignited, flame. Okay? Here I have some magic bottles. The bottles have been wrapped with black tape to prevent shattering. And in this bottle, you saw that reaction equation for hydrogen and oxygen? A reaction equation which I'm sure you all know how to write. A reaction equation which shows me that from a stoichiometric standpoint, the perfect way, so to speak, to make water by this reaction is to put together hydrogen and oxygen in a 2-to-1 mole ratio in favor of hydrogen. Okay? I've got that mixture in here. But I'm not getting any reaction. So I'm going to see if I can get these molecules to move about a little bit faster, because, for example, when I heated the paper with the match, that's really what you did. You get the potentially reactive particles to move so damn fast that bonds now will fracture and provide the opportunity for new bonds to form. Nothing. Does hydrogen and oxygen react spontaneously?
Yes.
How many of you are familiar with the historic event of the dirigible Hindenburg In 1937, German lighter-than-air ship, filled with hydrogen, came across the ocean, got tangled up with some electric wires over northern New Jersey, resulting in a problem. What was the problem?
It blew up.
The hydrogen, the Hindenburg, proceeded to disappear. Do you think hydrogen reacts with oxygen spontaneously? Well, we're not sure yet. But we demonstrated that paper reacts with oxygen spontaneously. But I've tried here, by this agitation process, to get hydrogen and oxygen molecules to react. I didn't get any place. So I'm going to try something else. To assist me, because I can't shake these hydrogen and oxygen molecules rapidly enough so as to give them the necessary kinetic energy they need. Do you realize when hydrogen reacts with oxygen? You should know about this. Hydrogen bonds have to break. Oxygen bonds have to break, while OH bonds make. But until you can start breaking the HH bonds and OO bonds, you're not going to get any chance for reaction. Well, let's see if I can do a little bit better, getting these molecules more excited, giving a better chance for these hydrogen bonds to break, OO bonds to break, and give a chance for this reaction to go by this heat process. Let's see what happens. I gotcha. Hey? How about that? Spontaneous, isn't it? Shall I do it again?
Yes. Yeah.
This is fun. Ready? Let's try again. Ready? Oh. See? What happens when you get these molecules more excited? When you give this thing the activation energy requirement, it goes. Okay, how about that? Now then, let's proceed. How about this reaction in reverse? Can I make this reaction go in reverse? Is this reaction spontaneous in the reverse direction? Well, if it's spontaneous this way, it can't be spontaneous in the reverse direction under these conditions. But can I make this reaction go this way? What do I have to do? The simplest way is to do this to it. That's the Greek letter omega, which to physicists and chemists means electrolyze. We'll dissolve an ionic compound in here, which will not react with water, in order that the resulting solution is... Why do I put the ionic compound in there? If I try to run an electric current through straight water, does that get me very far? No, why not? Ion concentration too damn small, isn't it? So I dissolve a little bit of ionic compound in there and up the conductivity, right? And now, when I run the electric current through there, I will readily make hydrogen and oxygen. Now, how about water vapor or water liquid at 25 degrees centigrade and any pressure you want, converting to water solid? Can this go? Can it be made to go at this temperature condition? Can this be made to go? Did in Chemistry 2045, did you study a phase diagram for water? Good. Now in your notes, right at the start of chapter 21, you have a phase diagram for water. Open it up. I think it's the second or third page in, something like that. Second page? Look at that diagram. Is it possible that I can convert water liquid or water vapor to water solid at 25 centigrade? Absolutely not. There's nothing you can do. So here's an illustration of a process which is not spontaneous if you maintain this condition, no matter what pressure you apply. Nothing you can do to make it go. Now how about water liquid or water vapor? In one case, water liquid becoming water vapor, or conversely, water vapor becoming water liquid at 25 centigrade. Well, I heard yup. Is it yup for both? Water liquid to water vapor. Under the conditions which are with us in this room, is that transformation, water liquid to water vapor, spontaneous?
Yeah.
What would you do to prove it? Now you can't see inside my cup, but I have good old aqua in here. Water. What would you do if I give you my cup and its contents being nothing but water from the drinking fountain, to prove that water liquid converts spontaneously to water vapor in this room, spontaneously? What would you do?
Heat to it.
Why?
Because
I want the conditions in this room. You add heat, you're changing the conditions.
What I do is I put it in a bottle and see.
It's in a bottle.
Oh, like
Called a cup.
closed bottle, and see if like
Closed bottle.
see if the edges become fogged.
Nope, I don't want you to put it in a closed bottle.
You just put a top on it, and
Top on it. Why do you want to put a top on it?
because then you don't touch the water vapor, so you can see it from the
Why don't you put a top on it?
You mark where the top of the water is inside your cup.
And
You come back in an hour or whatever and see if it's gone.
And will it?
Yes.
Probably.
Yes, it will. It will.
If the relative humidity in this room is such that the water liquid in my cup will not convert spontaneously to water vapor, then the relative humidity in this room is what condition? 100%. You want it to be 100% relative humidity in here? Do you want us all to sit around and stew in our own juices as we sweat? And there will be no net evaporation of sweat from our body surface, which means we're going to get warm and gooey and uncomfortable. But the air conditioning system does two things. Two things. It maintains a temperature at which human beings are commonly comfortable, usually around 22 or 23 centigrade, and keeps the relative humidity a good deal less than 100%. About 65% in here. Yes, that converts. Well then, if under these conditions in this room, this is spontaneous, this goes, how could this go in this room? What can we do to make this go? What has to be done to make this go, to make this become spontaneously? Do what? Increase pressure. If in this room, there's no water vapor in the atmosphere, I don't give a damn if you apply a pressure of 10 million psi. You're not going to make that go. Question. What does partial pressure measure? I want to know what partial pressure measures.
Like each individual gas will make sure it's clearing itself.
More specific. What does partial pressure measure? First of all, is partial pressure a property of gas, liquid, or solid?
Gas.
Gas only.
It's the pressure on a species of gas in the system.
What does partial pressure measure? You didn't learn this? Partial pressure is a measure of gas concentration in a gas atmosphere. Do you know that the partial pressure of oxygen in this atmosphere is about 0.21 atmospheres? And nitrogen about 0.79 atmospheres? Because this air is about 79% nitrogen and 21% oxygen. You learned this, haven't you? Yeah. Partial pressure measures gas concentration, which in turn measures tendency of gas to condense. Because the higher the partial pressure, the greater the concentration, and the greater the tendency to condense. What does vapor pressure measure? Liquid or solid. Vapor pressure measures the tendency of a condensed phase, liquid or solid, to convert to vapor phase. So if you want this to go, you've got to create conditions for which this exists. The tendency to condense by the gas has got to exceed the tendency to evaporate. Partial pressure water vapor has got to be greater than vapor pressure water liquid. Pick it up from this point next time.